Let's now think about some of the details and dimensions of the calculations when we're actually implementing training in a sigmoid network. So we're going to think about a 3 input, 1, 2, 3. Third one could be the bias term, in fact. A two-layer network, so it's got one set of activations here and one set of activations here. One output sigmoid network. In fact, we're actually putting in a bias term here to illustrate what you'd have to do. So the input size then, in this case, is going to be a 3x1 vector. Because we've got two outputs here in the intermediate stage of the network, the weight matrix is going to be 2x3, and the output at this intermediate level, there's going to be two outputs, so there'll be a 2x1 output there. Then we've got the activations coming out from the lower layer, which basically means the linear net sums, which are then passing through a sigmoid, giving rise to then these actual activation values. There's going to be 2x1 of those. What we're also going to do is augment then for the last layer in a bias term. So let's just go through the calculations of net 2 first of all. So net 2 is the linear output of the lower layer, and that's just going to be weight matrix W1 multiplied by the input vector x, so that's W1x. Like we said, that's a 2x3 multiplied by a 3x1. So we see from that the output is going to be 2x1. And it's matrix multiplication. And that's what it'll look like if we expand it out, just so you have a bit more of a feeling about what it looks like. Then, of course, we calculate the activations and the output of the lower layer. And to do so, we need to do an element-wise calculation. So if we say net 2 is the linear part of the output of the lower layer, then basically we have to use then net 2 is basically a vector, so we can calculate 1 divided by 1 plus e to the minus net 2 in MATLAB as long as we use element-wise calculations. So in order to get a bias term in the output layer, what we have to do is augment what we have coming out coming in from the lower layer. So we've got basically our A1 and A2, and we have to augment it with an additional 1 in order to account for bias. So A2 hat, as we're going to call it, is going to be a 3x1 matrix, whereas we started off with a 2x1. And of course the single value we've augmented is just simply a 1x1. So that's all clear. A hat 2 is 3x1. W2 is going to be now a 1x3 because we've got one output and effectively 3 inputs, right? And consequently, the linear part as well of the upper layer is going to be what we call net 3, and that's also going to be a single value, which is net 1x1. So let's calculate now the output activations of layer 2. First of all, there's this linear component, net 3, and that's just W2, which is this vector of weights, or this matrix, I should say, of weights in general, multiplied by the A hat 2. So W2 A hat 2. And that's what it would look like. It's going to have, as I said, it's going to be a 1x3 because there's 3 inputs coming in, right? And that's matrix multiplication because it's basically doing a weighted sum. And again, we've got the output. In this case, there's only a single value in net 3. So, but in general, this is also then the sigmoid is calculated on an element-wise basis. So it's basically 1 divided by 1 plus e to the minus net 3, which we can again do in MATLAB without any trouble. So the output then is a 1x1. In this case, then the target's going to be a 1x1. So we can calculate the output delta term quite simply. Delta 3 is going to be given by the output error term, and then the contribution basically from the differential of the output layer sigmoid. Right, so we should have seen this before. So we've got the minus target takeaway output multiplied by 1 minus output, and the delta 3 is going to be this output delta term, and we're going to use that as well when we calculate delta 2 for the lower level. So let's think about the size of these things. Well, in this case it's a 1 by 1. In fact, everything's 1 by 1 all the way through. If they weren't 1 by 1s, we'd have to do them all element-wise. Right, so they are actually all element-wise multiplications. You won't notice it if you implement this single output. Whatever you do, it's going to work. But you do have to care what kind of multiplication it is when you start ending up with multiple output networks. Okay. So A2 now is the unappended activation outputs, and we're going to call W2 hat. We're going to call that the effectively relating only to the weights which actually go back to actual output nodes. We're not so bothered about, well, we don't need to calculate now what's going to be the effective error at the bias node, right? Because we know that value is going to be 1 whatever we do. But we do care about what the effective error is going to be now at the output of the first layer. So we need to back propagate, and to get this delta term, what we end up with then is this back propagated term, which is the delta 3, which effectively is the error at the output, back propagated through the transpose of the W2 weight matrix, and we saw that before. And then we have to account for the fact that we've got a sigmoid here on this output here as well, so we have to account for the sigmoid function in this term here. And in this case, of course, the output is A, so it's no longer O. So in this case, we've got the A2 times 1 minus A2 activations. And this is then, the error back propagated to the lower level. Basically, we've now got, by doing this, we've effectively defined what the error is to the lower layer. So A2 is a 2 by 1, W2 hat is a 1 by 2. We end up then with, because basically we only need to change those weights. We calculate now all of these terms like we've just explained from that equation. We calculate W2 transpose delta 3. And in order to, so in order to basically calculate the effective errors then at A1 and A2, we don't need the full weight matrix W2. We just need basically the one that relates just to the first two terms, and not the term that which actually relates to the bias. So that's what we're calling the W2 hat. Basically, this is just weights feeding to the lower level, and we're not including the one which feeds to the bias, because we don't want to calculate the error at the bias, because we don't want to do that. We know that's 1. So that's where that comes from. So basically, if W2 hat is just the first two terms, right, this term here and this term here, the third term we don't need, this one we don't need. So W2's got 3 terms, W2 hat has just got 2, and of course if we transpose it, it turns into a column vector. So this is a column vector times delta 3, right? Again, the output here, this is just like we did at the overall output, is all done by element-wise multiplications, because we've got to deal with the sigmoid. In this case, it's all 2 by 1. And also, like we just said, now W2 hat transpose is also 2 by 1, right? So it's all nice 2 by 1, and delta 3 is actually a 1 by 1 because we've just got a single output. Therefore, delta 2, as we expected, that's what basically the effective error, which is at the output of the output of the lower layer is just going to be represented by what the error is at A2 and what the error is at at A1 and A2, and that's therefore just 2 values. So that's going to be a 2 by 1, and that's a matrix multiplication in there. So basically then what we want to finally do is calculate the error gradients with respect to W1, so we can do gradient descent. So dE dW1 is going to be delta 2 times the input to that layer, so it's basically the effective error at the output of the lower layer multiplied by the transposed input, and that's going to be a 2 by 1 times a 1 by 3, so we end up with a 2 by 3. We can see that it's got to be the same size as the weight matrix, right? That's always the check that you can always make, because this is basically the differential of the error with respect to W1. It's got to have the same dimensionality as W1, and that's a matrix multiplication in order to get that to do the right thing. And then, of course, the error gradient with respect to W2 is the output delta term times by the effective input to that layer. So in this case, it's going to be delta 3, which is 1 by 1, because we've just got the one output, and we've got then the appended input coming in from the lower level, which is the 2 activations that's been appended with a 1, so we end up with that as being a 1 by 3. And overall then, we'll end up with a dE dW2, which is 1 by 3. Again, that's got to be the same size as the weight matrix in the second layer. So in order to move the weights then, we have to, or update the weights, we just move them in the direction of the negative gradient. So W1, this matrix W1 here, we just basically say W1 equals a scaling factor multiplied by the gradient of the error with respect to W1. So that's a 2 by 3, that's a scalar, that's a 2 by 3. So effectively we just have to multiply all those together element-wise with the alpha and the gradient in order. So we basically scale each element by alpha. And we end up with a 2 by 3 matrix, of course. And same kind of principle for W2. Again, we move down towards minimum error. So W2 goes to scaled version of dE dW2, which is the gradient of the error with respect to W2. In this case, you can see it's 1 by 3. So that's, again, 1 by 1, because it's just a scaling factor. 1 by 3, which has got to be the same size as the weight matrix. And again, that's element-wise multiplication, so it's just scaling every value in the gradient vector by alpha.